Okay. So can you guys see the slideshow?
Yep.
Okay. Nice. So we're going to be going through a whole bunch of introductory kind of concepts, and then we're going to talk about the our setup and how we're kind of our solution to like our test stand. And let's get started. This will be assuming you know what a computer is, you know what internet is, you ideally you've done some coding before. Like you know the when I talk about memory in general, I'm talking about RAM. So that's live volatile memory. That's the portion of your computer that is like if you unpower your computer, that memory is lost. So it's not your hard drive, it's not your SSD or HDD. It's like when you open up Task Manager and it says memory like 50%. That's what I'm talking about. There is also non-volatile memory, which is kind of annoying. When I talk about that, I'll try to refer to it as like flash drive or something, because usually what we use in embedded systems is a form of flash. Try to keep the chat open. So ROM is that's a form of non-volatile memory, because like ROM stands for read-only memory, and like you can't really write to it while running, and so every time you shut it off, it'd have to be kind of reprogrammed. I'm sure there's some form where like it's automatically programmed on boot or something. Maybe. I guess for now, assume that ROM just means read-only memory, whether or not it's volatile or not. And volatile means if you turn off your computer, then that memory is lost. Non-volatile means if you turn off your computer, you still have that memory. And this will be assuming you know some stuff about C and C++. So like data types and structs, variables, how to assign variables, what a variable is, like, you know, kind of how memory is structured. I'll go into more detail later. And lastly, what pointers are. So pointer to a memory address is memory is one big contiguous block of like storage locations for bytes, and a pointer is a piece of data that gives you an address of a certain byte or series of bytes. And so it's important to like know where information is and like be able to like pass on the location of information, so you don't necessarily have to always just move that information directly. Okay, what is a microcontroller? A microcontroller is a like embedded kind of very not as powerful, but it's like a system on a chip. So it has all the components like a CPU, memory. It often has flash. It has serial interfaces and stuff. It also has like, or it's very rare that a microcontroller won't have what are called GPIO ports, or like ways to interact with its environment. So your like desktop computer or something, there's no way for you to like easily actuate like an LED or something. But these microcontrollers often have pins that you can programmatically turn them off and on with code, and you can often do this very quickly. And on the right, we have the Arduino Nano. The Arduino Nano refers to the whole board and everything along with it. And this, like, Arduino has made a bunch of open source, like, I think the word is breakout boards for these. It's basically the microcontroller with like an external oscillator, some resistors, power management stuff, and like a bunch of interfaces, like the USB and like having lines and holes to all the pins. But the actual like microcontroller on the Arduino Nano is an 18 mega 328. So if you want to know the specifics of the like internals of the like thing powering the Arduino, you Google 18 mega 328 datasheet. And this is different from your like base computer, because your base computer, like you have the processor and RAM and stuff and like hard drive, that's all separate. But also like your base computer is generally running like a general purpose operating system, whereas a microcontroller, you can port types of simple operating systems to them, but a lot of the time you'll just be running like one piece of code, and that'll run as soon as you boot it up. It'll like load from its non-volatile memory and start running. And the only way to reprogram it is through like there's a number of ways to reprogram. Okay. What is an operating system? An operating system is basically a program that manages all your other programs and acts as an interaction layer between your software and hardware. So I have a like picture on the right where it's like your operating system will manage your memory and it'll allocate it to different programs that need it. It'll like it'll block programs from accessing memory that's not theirs. It'll shuffle around memory and like have a layer of abstraction. So like your program itself doesn't need to worry about where its memory is. The operating system will take care of that. There's IO management. So like when you tell, excuse me, on a Raspberry Pi, when you like tell it to flip a GPIO pin on and off, there will be like a few layers of interfaces that your software will have to go through your operating system to flip that pin. Resource management, there's a lot of resources, and like often it's not just like CPU time, it's access to like a USB device, or like being able to write to a file, for example, because like when one program opens a file, it sort of you can't really have two programs easily write to the same file at, like in the same instance. So there will be like some passing on, like you'll have to update them, make sure they're like both aware of stuff. And that's part of file management as well. Security management, that's less in the form of like cybersecurity, more in the form of managing which programs have privileged access to what. And that's mainly so you don't screw up your own kind of computer, or you like you separate the types of programs or access into like kernel level, which is like higher access, and user level, which is like lower. Actually, technically kernel is lower access, but lower as in more privileged, and user is higher access. So the kernel level programs can directly access the registers that and drivers that do stuff with the like hardware, and like they can manage the like data structures that hold information about what programs hold, like holding what memory and stuff. And you don't want to be able to change that manually, whether intentional or not, through like your user level program. And command interpreter, it allows you to run programs dynamically. So like you don't have to have everything running on boot and stuff. And so on the left, there's another diagram of the kind of abstraction. So the important thing to remember is the operating system is a program that manages all the other programs and processes running, and it also acts as a layer between software and hardware. And oftentimes when they design CPUs, they design them with certain operating system architectures in mind. So it's a special program. So most of you are probably familiar with Windows or Apple. I'll talk about Windows specifically. Windows is your operating system they run on, and it'd be like Windows 11 or 10 or whatever. It's all paid and proprietary. They don't let you have access to the source code. Microsoft has a lot of staff it needs to find work for, so they often dump a lot of features into this. And like it's a lot of stuff that you may or may not like want on your system. Like if you have like a really beefy computer, which most computers for like office work are pretty beefy for like what their purpose is, then like it's fine to put like random stuff on it. You can make them really complicated, but that's kind of bad for like high reliability systems, is because that means there's a lot of things that can go wrong. And these are all maintained by Microsoft. There's no like outside private party. Yeah. Linux, on the other hand, is a free and completely open source kind of base of an operating system. And like open source literally means you can like open up the source code on like there are, I think, GitHub repos by the creator of Linux who is just like hosting the original Linux source code. You can like download it, compile it, and run Linux. They, in general, their design is like they have a like a Linux kernel, which is like running your like most base level process memory management and like IO abstraction and stuff. And then you can customize it a lot. So you can add what are called modules to it. If you need certain functionality, you can like you can customize it higher up more so. You can technically like take the source code and like rewrite a lot of it, and like it'll be Linux, but like it'll be a modified version. And this is what a lot of people use for like embedded systems. So like your routers, smart TVs, Teslas. In aerospace, it hasn't been traditionally used, but it's seeing more and more use as like there's a lot of like support for it. A lot of people know it, and like it's a very powerful tool. It just like if you want to use it in aerospace, there are certain modifications which you'll need to do to hit like timing constraints and like reliability stuff. But in general, it's like it's a very versatile operating system, and they're released in distros or like distributions. These are like Ubuntu, Debian. Those are the two off the top of my head. Basically, different organizations like host and maintain their own versions, and like they release their own updates for it. And like right now, the Raspberry Pis are running Raspbian, which is a kind of like shrunk down a little bit version of Linux, and I think it's based off of Ubuntu or something. But like, whatever yeah. Other examples of operating systems are Apple. Obviously, they have their own. It's even more closed off than Windows. There's some benefits to it, but like you'll basically never use it for like embedded systems unless it's your iPhone, which is going to be in all likelihood a modified version of Linux. FreeBSD is not a Linux kind of shoot off. It's just like somebody made their own. Now VxWorks and FreeRTOS, these are what are called real-time operating systems. These are much less I'll say complex versions of operating systems, but they're like designed and like chopped up in a way to be very strong with timing constraints. They don't have nearly as many features as the other ones, and they aren't nearly as dynamic. And they require a lot more like thought put in when you're like designing stuff, but they will have like precise kind of reliability. And these are the ones that are, well, specifically VxWorks. FreeRTOS is just like a free version of a real-time operating system, but VxWorks was for a long time the de facto. This is what you use if you have a computer on an aerospace system, because you need to hit time constraints. You don't need to have Microsoft Office or something, but you need to be able to like actuate your wing whatever flaps at the right times always, or you fall out of the sky. Okay, so in general, your computer is going to run like a whole bunch of programs at the same time. Like right now, you're probably running your like UI, whatever. You might have like a Internet Explorer or something open in the background. You're clicking through. You're also watching this lecture on Zoom in a like another window. And then there's a whole bunch of other stuff going on in the background. That's like scheduling updates, looking like ping, whatever. In general, how this works is through scheduling. And so most resources are scheduled in some way, but the one we care about most is the CPU scheduling. So on the right, I have a diagram where like when you have program or processes running, or actually I'll go over the definitions real quick. A processor or CPU is something that runs your programs. A process is a running instance of a program, and scheduling is the method you decide what process runs on what processor at what time. So you have a series of processes. How do you decide which one runs? Because in a processor, you can only technically run one thing at one time instance. So what do? You chop up your processes into time slices. And then you like feed them into this queue. and then your scheduler will decide which process gets to run on what processor at what time. And oftentimes these time slices are in the microseconds. So they're very, very short, and they switch it very, very quickly. And they switch so quickly that to you, it seems like they're running at the same time. And so this is in the case of one processor. In like multiple physical processors, it gets a little more complicated, but we won't worry about that right now. But like, as you see at the bottom, like every time you have your process A run for a period of time, it needs to switch. And like, there is some overhead involved with switching. Like it takes a little bit of like computational work to switch these. In general, it's pretty fast, but like general purpose operating systems are optimized to make sure that these switches happen in the most efficient ways. So what it's trying to do is it has like the set of processes. It assumes they're all roughly equal in priority and tries to get them the most processes through the choke over a given period of time. This is, in general, fine. On our current test stand system, we're going with this method because like the schedule is really complicated. And like we have enough processing power that we can kind of brute force it. Like we're not missing any time constraints for us, and like our time constraints are very lax for it because like we're not flying, so our control system is not inherently unstable. So like if we miss it by a few microseconds, it's not a big deal, or like milliseconds even. If you guys have any questions or something, just like interrupt or raise your hand or type in chat. Here is just a demonstration. Like every time you want to switch processes on a processor, you need to save the states in it says PCB. This is a process control block. It's just like information about a process. You save the states in it and you like move it into memory, and then you take the other process and load it from memory into your CPU and then run it for a few milliseconds. And you do this really quickly. And like there's a lot of code optimization that could be done to make this more efficient. This might seem like a trivial thing, but like this is a really important concept in embedded systems and especially embedded control systems. Because again, you want to make sure the things you need to run in a certain amount of time are able to be run in a certain amount of time. So yeah. Memory. So memory, main memory, whatever, RAM, volatile memory. This is memory that technically, or it exists outside of your CPU. Your CPU has like, they're called caches. They're like very small portions of memory, which are used to like make things more efficient. But in general, most of your memory, so like all the stuff that's currently running, I guess all the stored information of currently running processes is in your main memory. And so on the right, you see there's like a diagram, the virtual memory. So like this is assumed to be memory for a given like single program. And like if you the reason it's stored like this is because like literally numerically it goes from like 0 to whatever XF whatever, like the hexadecimal size of your memory. Like these each chunk of memory, each byte has like a numeric memory address. And so in your program, when you refer to like memory locations, you'll need to kind of, you don't need to like hard code in memory locations, but you'll need to like be aware that these memory locations are often next to each other or they're like stored in certain ways. In what the operating system does is it maps your program's memory space from 0 to, let's say 100, and it maps them to different chunks in physical memory. So it might be like 0 to 30, and then 60 to 70, and then 90 to 150 or something in physical memory. But from your perspective as a programmer, it's only 0 to 100. Now, another important thing is if you try to access memory outside of what you're allotted, your program will immediately crash, and it's called the segmentation fault. This is one of the most common ways to crash your program, and it's important to be aware of what memory you're accessing. And also, when we get more into operating systems later in the semesters, I guess, like later in the months, this is something that we might have to like manage ourselves. When we get to simpler operating systems, they might not have their own like guards against you accessing bad memory. Okay. And these are just examples of non-volatile memory. So it doesn't have to be just your hard drive, like spinning whatever hard disk on your computer. It could be like different things. The main thing we might use as an external non-volatile memory is an SD card, like an insertable one. We are probably for now going with like onboard flash memory. So that's like soldered onto the chip that we'll be using, and like to access it, we'll have to plug it in and like go through a little bit of a serial interface. It shouldn't be too bad. Again, kernel space versus user space. So every program and every memory location, like the memory locations are sort of what are called pages and segments stuff. That we don't need to worry about that right now. Just assume that every program is gonna be operating in either kernel space or user space at a given time, and every kind of memory location is either going to be part of the kernel's privileged memory locations or the user's like whatever memory locations. And in general, if your process is running in kernel mode, then it can access pretty much any memory location, or at least any kernel memory location, I think. And also it has privileged access to things like hardware. So in general, how the pipeline goes, if you want to access hardware, is your regular program executes what's called a system call. And that system call is a basically handoff that the program says to the operating system, hey, let's say I need to read from this USB or something. And then your operating system says, okay, I'll do that. And it grabs the sort of information it needs and it sets itself to kernel mode, and it like runs that information or gets that information and passes it back to the like user space program. And if you remember from before, whenever we switch processes, it takes a little bit of overhead. So in general, like this is something you'll also want to be aware of when running like operating systems with multiple processes, is every time you do like this kind of privileged access, it'll require a context switch. So this is why it's important to be able to kind of be aware of memory and memory access, is because in the event that we don't have this kind of there might be a case where we want to avoid having to switch between kernel and user mode and like doing this entire context switch and just directly accessing the hardware, because it's more efficient, but it takes more consideration from us. So like I'm trying to tie these concepts together. Again, if you're like, I don't know, if you have any questions, ask. And another thing, kernel space has the like information to run the processes and the OS. So stuff like the PCB is a process control block that actually has to be stored in memory somewhere, and so that's stored in kernel space. And it's like it's literally like a C data structure, at least in Linux. It's a C data structure that like says like, okay, there's one for like every process, and this process has access from this memory location to this memory location in physical memory, and it's like currently in this state, it's idling, it's waiting for the PCB or for the CPU or whatever, yada yada yada. Again, you don't want to be able to change those values. You want those to happen automatically by the OS. So you as a user don't want to change it. Hardware interaction. So there are a few different ways. On the left is an example of how Raspberry Pi does it. It has, again, memory locations that the CPU accesses. So on the left are the addresses, and these are the physical addresses. And as far as I'm aware, you need to be in kernel mode to change these. And each of these correspond to like a 32-bit number or whatever, 4 bytes, whatever. For now, it's all numbers. It's all ones and zeros. So like what happens when, I don't know if you guys have used Raspberry Pi, but in code, when you like want to change one of these pins from voltage 0 to voltage 3.3, you need to like type, okay, digital write the pin number and then high. What that does is the digital write interface passes this information, like it does a system call, and that system call sets the like the proper register field number to the appropriate value. And then after that like register is set in memory, the GPIO hardware reads from those registers. And like again, bits are technically like physical voltage levels in the computer. So there's associated hardware that like reads that voltage level as a gate and outputs that voltage. But from your perspective as a programmer, all you did was change memory location, and that flipped the GPIO pin on or off. This is one example of hardware stuff. Another example is like in the top right, I guess. It's a more abstracted version. So like if you need to talk to a printer, you don't really know how that printer works, but there are drivers that your computer already has that allow you to talk to your kernel to talk to the printer. So your user program says, okay, I need to print this, and then it makes the system call to the certain device to like write to that device, and then the system call calls the driver, and then the driver parses that information, sorts it out properly, does whatever, yada yada yada, and sends it off in a way that the printer can understand to the printer. And this is done in kernel space. Yeah, Devin.
So like what exactly is a driver? So does a driver have like, does it store memory?
It can. A driver is a software interface for hardware to that is run in like kernel mode. And like we technically, if you want to stretch the definition, we already have drivers for stuff like SPI. It's just it's just a matter of whether or not it's run as part of the operating system or run as part of like our program. Linux, for every device, it has like places for you to load drivers, and we might end up writing our own drivers. So far we haven't had a need to, but this is just to be like aware. It's a way to kind of abstract away from the user space the like hardware interaction. And you see at the bottom there's like, this is an Ambarella chip. Ambarella is just like another manufacturer or whatever, but they run like Linux operating systems often. And you have the APB interface. I don't know what APB stands for, but like you can think of this as the like kind of, how do I say, the system call interface between the, I guess, user space and kernel space. So that takes your command to like set a GPIO, for example, and that APB interface writes to the GPIO register, and then the software drivers are like reading from those GPIO registers and like doing whatever processing is needed to like get the right GPIO pin activated. So is an electron? Okay, yeah, there we go. It's a kind of bus, I guess. Okay, GPOS versus RTOS. So I'll go through the points step by step. As I said before, GPOS, so general purpose operating systems, are things like Windows, Linux, and Apple, and FreeBSD. And then RTOSs are things like VxWorks and FreeRTOS. Those are the ones that have very strict timing constraints, but they're in general like less complicated and they are more reliable, but they're like less throughput. They're less efficient with like general use. So unfair scheduling in an RTOS, like every process in an RTOS has like a hard-coded priority. And if you see on the top left, every time a high priority process wants to be run, and there's a low priority process running, then the high priority process will preempt the low one and like start running. And an example of real life would be, you have a rocket's control system process that's calculating the like minor thrust vector adjustments given the like sensor data, and this needs to be updated every 50 milliseconds because that's what you design your control system to be. it can't wait for you to finish like transmitting data packet. So like you'll have to stop halfway through your transmission to make that adjustment on the whatever computer and then continue transmitting, as an example. If you want to like more like personal example, if you've ever opened up something and like it's needed to update or like something happened and like your computer froze, like imagine opening up, I don't know, your email app and then like your computer freezes and like you can't like open anything else. Imagine that happening, but on an airplane where if you don't like actuate your stuff in the right time, you fall out of the sky. So we can't have that. So that's why we go through and like use this. Typically want to use this RTOS model. Another thing in RTOS is the kernel is preemptive. So like typically kernel level programs are never preemptible. And so whenever you make those system calls, there's no way for another program to interrupt it. This is there might be exceptions to this but as far as I'm aware, this is a general rule. And at the very least, no user level program can interrupt a kernel level program or preempt, whatever. And so like the kernel level programs will always have whole priority in a general purpose operating system. That's not the case in RTOS. Again, like even if the kernel has to like fetch some hardware files or whatever, and like in a general purpose operating system, this would have priority. But again, you don't want to fall out of the sky. So your user space control system one will have to be able to preempt that. That's one thing that might have considerations that you have to watch out for, but for now, just like be aware. Priority inversion. This SparkNotes version is like if you see in the top left, imagine the like the low priority process places a like lock in software on a certain resource and says, okay, for now until I release this lock, no one else is able to use this resource. But if the high priority process starts after this low one gets the lock, and then the high priority process, let's say, wants this lock, the low priority process is unable to release that lock because the high priority process is running and currently waiting for the lock that needs to be released, but it's unable to get it because the low priority process will never run. And so this is something that we really need to consider. In general purpose operating systems, there are mechanisms to avoid this, and like there's like dynamic scheduling and stuff. And if a process is locked for too long, like waiting, then it just like switches, even if it has technically a higher priority. But this is when we get into like mutual exclusion and stuff and like whatever, this is something we'll have to be aware of. And lastly, RTOS is predictable. Yeah, that's the whole goal, is to make everything reliable and predictable. We don't care as much about throughput. So like you won't be able to run a video game on an RTOS, but you'll be able to run a control system. And in the bottom left, in general, you can run RTOSs. They're like often a lot of them are made to be run on microcontrollers. And like you'll have all the RTOS stuff in like one program, basically. Like you'll have different like functions as like sub process kind of, or like tasks. And like you'll have to run these at certain times, and like often these are event driven. So like you have your loop where it's stuff that you don't really care about hitting real-time constraints. So like the example would be like transmission. So like in our RF project, let's say we're in the middle of transmitting a photo and we need to get sensor values. So we like stop that transmission, we trigger the event like, okay, 500 milliseconds have passed since our last sensor update. And so we preempt the transmission, we run the sensor update stuff, and then we go back to the transmission to continue running. Yeah. Serial communication. So in general, a lot of the ways that different like devices communicate with each other is through serial communication. And this is everything from the like how your CPU talks to your memory bus or your RAM itself, all the way up to how like my computer is parsing the bytes into like on and off to pass through my internet cable to get to you guys. And even like how your video card transmits to your display, that's like just a really fast serial data communication. And so they all work. So they all work with, in general, they all work with a clock and data. And you see every time the clock goes low, from high to low, so that's like a clock ping or pulse, it reads the value of the data line. And so you see if it's high, it's 1, if it's low, it's 0. And like this, with this clock and with this data line, we're able to transmit 11001010. And in ASCII, that corresponds to S, the character. And just to be clear, these high and low values, like this is a graph where like the horizontal axis is time and the vertical axis is digital logic. In real life, this is a voltage value. So it'll be a voltage value from 0 to 1. And we won't go into like the hardware of how this works. It's with what are they called? Transistors. Technically like MOSFETs, transistors. It's turning gates on and off really quickly to allow and disallow a voltage level based on what like your internal computational logic determines. Okay, so SPI is probably going to be the main way you talk to other stuff, and it is a very, very commonly used thing, especially for, if not hobbyists, then also professional stuff and like general low to medium throughput devices, and like complexity. Basically, how it works on the left is we have our transmitter and receiver. If you see in literature, it'll be controller and peripheral or master and slave. If you see any of those, like MOSI is master output slave input or controller output peripheral input. It means the same thing, just to be aware. Okay, so how SPI works is we do the same basic transmit and receive, but like when you like all the SPI devices are connected on the same clock and the master controls the clock. And so every time you want to send information, the master will bring the chip select line down low for a given device, because normally they'll all be high, but like the chip select is how you select which device you're talking to because they're all wired to the same like wires. The chip selects will be individual. You bring it down low to select for a given device to the selected device, and then you have your transmission. So the serial clock will pulse on and off for a given number of bytes. And then at the same time, bit by bit, the master will send out a bit and the peripheral will send back a bit. And like this happens in the same clock pulse. So like when you see in the bottom right, it says wiring pi SPI data read write. So there's no distinction between reading and writing. It's when you have an SPI transaction, it both happens at the same time. The important thing is to be able to read the data sheet and see what bits matter and what don't. Because often like you can only send 8 bits at a time, but like I think for our ADCs, for example, we have the first like 4 bits that the master sends out be an address channel, like a channel address value and like one setting value. And then the rest of the, what is it? The rest of the 12 bits are like the data received from the like peripheral. And you might be asking, Marco, that's one transmit and then one receive. Technically, you're receiving those first. The peripheral sends out 4 bits as you send it 4 bits, but you don't care about those first 4 bits. Then after that, the peripheral will continue to send out 12 data bits while it's technically reading from the line the following 12 bits from the master. But it just doesn't care about those. So this is just like a kind of important concept to wrap your head around. The transaction happens, I'll say, at the same time. 1 bit is pushed out for every 1 bit received. It's just a matter of aligning those bits right and processing them so you get the right information. And so, yeah, at the bottom, it's the code we have. It brings the chip select line low. You package your message in bytes, and we use unsigned characters because that's a single byte, that's 8 bits. And in this case, it's to write to our IMU registers. So the first 8 bits are the register address, and then the next 8 bits are the write value. And you put this in what's called a buffer. So that's MSG2. It's a 16-bit buffer, and you put that in a memory location, and then you call the wiring pi function to read from that buffer. So it takes those 2 bytes, it sends them off, and then at the same time, whatever it received, it packages and puts back in that buffer. So every time you do this transaction, your buffer will be, the information in your buffer will be, or the amount of bytes that you assign, so in this case 2, will be sent off to the peripheral, and whatever it received at the same time will be loaded back in that buffer. And so in our previous ADC example, we only care about the bottom 12 bits of, and not the like first 4 or whatever. But since it's in bytes, it's the full 8 from the second byte, and then the bottom 4 from the first byte. So we care about the bottom 4 from 1 byte and the whole 8 from the second byte. And so that'll involve you like masking out the top 4 bits of the first byte, because that might be anything. And you need to like align them up, and you need to kind of store them both in the same data number to get like an actual number. We can talk more as you guys go with this problem, but this is like something to consider. It's all just bits and like memory. So like you just need to like shuffle things around, make sure they're like lined up right, and like read them the right way, basically. I2C is similar, except that instead of having a chip select line, all these data and clock like masters and peripherals are on the same. So all the datas are on the same line, and all the clocks are on the same line, just like SPI, but there's no chip select. So you might be asking, how do you select which device to talk to at a given time? That's done by the information in the data. So here we have, you see the 7-bit, can you guys see my mouse?
Yeah.
Okay. So we have the 7-bit address. This actually, every peripheral device is going to have an internal address defined. And so it's constantly listening on this data line for its address. And so how you decide which device to talk to is your message will be an address followed by some setting or whatever consideration bits, followed by your data, followed by like an ACK or like acknowledgement bit or whatever. And what this means is it is a lot simpler from the hardware side, and but it's much less efficient, and it's more prone to errors from the like data communication side. So like in theory, you can fit as many of them as you want on like the same wiring, but like it'll be dependent on how many addresses you have and the ability of your controller and peripherals to send that information without error. And also another thing to consider is in SPI, all of the bits or the majority of the bits are like information related to your transaction. So if your SPI device can handle, let's say, a megabyte per second, then 100% of that megabyte per second can go to whatever, the transmitting of data. Whereas this, if half of it's just for the address, then you're only able to access like half of the information. Half of the bandwidth, I guess. And one last thing to note is with both SPI and I2C, these things are often switching very, very quickly. And so like the clock frequency we're using is something in the like 2 megahertz. So this clock goes up and down 2 million times a second. And this chip select it's technically the slowest part of our current setup, because we need to go through the like, we use digital write, so it needs to go through the system call and then the context switch and drivers and stuff to turn these stuff on and off. And on Raspberry Pi, that's kind of slow. But even then, this is switching like, I think in the kilohertz per device. So like it hits every device, let's say like hundreds or thousands of times per second. So like these are all very, very quick. And so we want to make these efficient. USB is a step more complicated. Oh, yeah, Devin.
Go back to the last slide real quickly.
This-
So there's an acknowledge bit right after the address is sent. Is who's sending that acknowledge? I'm assuming it's the slave, right?
I'll have to check. I don't. Yeah, at the bottom you see. So
Yeah.
it says master is for the address, and then it has the slave acknowledgement, and then again master sends it out and slave acknowledgement.
Okay. So we can only send 7 bits at a time, correct?
Technically, I think it's 8 and 8. So I think it's 9 total. So like 7
Oh,
or
I
8
see.
from the
Okay.
master, and then yeah, which is another thing that slows things down. And like every time you need to, in general, every time you need to switch who's talking, or like do something that's not directly sending bits in the like data line, that'll take some overhead and slow your system down.
Okay, so that's probably the main difference between SBI and, or aside from the
Address.
yeah,
Yeah.
but it's
Yeah.
probably the main difference between I2C and SBI then.
Yeah.
Okay.
This is another very common one. So often there will be a lot of drivers that already support this information. It's just something you need to be aware of. USB is more complicated. It is a serial device. So S in USB stands for serial, universal serial bus. It does the same thing where it has but it's more complicated, and there's a lot more like internal settings you can set, and like there's a lot more code in the driver, basically. It's typically used for bigger data transfers, but like not as frequent ones. So you have the preamble, that is like information to set the whatever USB connection and stuff. The address is for the address of the USB device. Header is here, you can see at the bottom, like the size, the ID, whatever. SOP stands for start of packet. Yeah. So like it says where the start is, and like there are like pages and pages and pages of information about this protocol. And then the data is the next few, like however long bytes as defined by your header. And then CRC is error correction. So it's to make sure that the bits you send is with a very confident probability the same as the bit you received. And like when we do the RF stuff, some of our bits will have to be CRC bits. And so like we might end up having a similar kind of setup where our transmission involves a header, as in like what type of data transaction this is, whether it's like sensor data or like image data, and like how big it is, what rows of pixels in the image or something, and then like send the data, and then have like CRC bits, which if our CRC sent and received don't align, then we know something went wrong. And then there's the end of packet signal, so you can say like, okay, this is done. Ethernet is even more complicated, but it's in a similar style where it's like you have prefixes to tell you information about like what you like this piece of data, and like you have your CRC at the end. It's the same concept. It's just you see at the bottom, this is layered. So like as it goes from like the different protocols, each protocol adds like another header on top of it. And so like even for small, like this isn't something we need to worry too much about, but this is just like to have an idea of how these serial communications get more and more complicated. And if you want to read it in detail, you can read like there's like IEEE something or other. They release like standards for this internet protocol format. But in general, for our purposes, we don't care too much about it. Internet. The highest we'll probably touch is like bit by bit, or how we care about this formatted is like USB or whatever format we use for RF. Secure shell is another protocol that acts on top of internet, and it's a way to through like encrypt or securely or encryptedly log into a remote computer. And this is the primary way we connect to our testnet. So we run an Ethernet cable, and then that Ethernet cable, like we set up our local area network, and then literally the same as when you send in like log onto the internet or something. It's the same IP format. It's just instead of using HTTP as the format or as the protocol on top of IP, we use SSH. And so instead of like going into Google and like YouTube or whatever, we use the internet to log into our test stand remotely. And this will involve you'll have to log into the right IP address and like type in the password for the user, and then the host machine will also have to be running the like SSH server to be able to be listening for those like SSH logins and be able to like transact your commands and like send and receive stuff. In the bottom left, you see there's a like it looks like a chat log. This is how you actually, or this is the main way we'll be talking to our like Linux-based machines is from the like control computer. It's what's called the command line, and you type in commands to control the computer, and everything that you'll need to do, you'll be able to do through the command line. The one thing though, for the, I guess, live video and GUI teams, you might have to care about the internet stuff. So like the base internet protocol is what you'll be doing, but in order to get it, let's say, in order to port the sensor data into like the LabVIEW might only be able to take certain types of like IP protocols. So like how do I say this? Yeah, some application layer protocols. So instead of HTTP, it might only take like raw socket data or something. I don't know. We can talk more. I've done some internet stuff. I haven't done like a huge amount, but like this is why it's not just a like front end project. It'll involve some networking stuff. Same with the live video stuff. Our system. Okay, we're finally here. This is our physical system setup, and I'll go through image by image. On the top left, it's what our rocket engine looks like. And this was in our wet dress rehearsal 3. So we were using liquid nitrogen and water for our test as stand-in for liquid oxygen and ethanol. In general, how we have it split is our left side is for liquid oxygen and our right side is for ethanol. And so anything on the left side, so the lock side, is going to be even numbered for the solenoid valves, the hand valves, and the pressure transducers. And anything on the right side is going to be odd numbered. So anything for the ethanol stuff is going to be odd numbered. And the one thing to be aware of is currently we have SOV4 and SOV3. They might be a little hard to see in the bottom right. Those are our pressure bleed off valves. So in the event of an emergency or in the event of like pressure control, those are the valves that we're going to be needing to control to be able to sort of regulate the pressure by expulging pressure at, which in this case is nitrogen with some gaseous oxygen mixed in. And here we have SOV2 and 1. Those are the pressure lines. So when we open those, they pressurize the respective LOX and ethanol, and we'll need to open those and close those at the right time to get the ethanol and LOX pressures right. And there are some other like hand valves which are for purge, like there's the nitrogen purge tank, which when we open that valve, it like blasts nitrogen through the chamber so that we can like turn off our engine basically. So we can flood it with non-reactive gas that suffocates the fire, and then we like stop our ignition. As for control, we have our control laptop. This is, so far it's been Gavin's laptop. We have the like SSH client and stuff set up in the local area network, and we just plug in Ethernet and run it to the Raspberry Pi on it. and then it automatically we're able to connect as soon as it powers up. The Raspberry Pi is connected to an onboard Arduino through USB. This is its watchdog. So watchdog is basically a timer or like a, yeah, I guess a timer that it pings the Raspberry Pi every however long. I think it's like 1 second, half second, whatever. And if it doesn't receive a response in a certain amount of time, it reboots the Pi because it assumes that the Raspberry Pi has stopped function. And this is kind of like a backup safety system. And like we'll go into it more a little later. It's by its name, watchdog. It's meant to be watching the Raspberry Pi, making sure it's working and rebooting it if it doesn't. And there are typically internal watchdogs on most microcontrollers and Raspberry Pis and stuff, but we needed an external one for to be able to enact certain like logic processes and like control the test stand even when the Raspberry Pi is not working. Because typically this watchdog, like an internal watchdog, all it'll do is if the process or if the CPU blocks for too long, then it just like reboots. And this could lead to a boot cycle where if you messed up your code, then you'll just continually reboot, and then we can't do that because we'll lose all control of our test stand, and that's bad. And this Ethernet cable is really long. I think it's about around 250 feet. I don't know exactly how long, but yeah, it's like this example is close, but if you see in the photo, we're going to be like, I think near the tree line. We have a spot set up that we like measured out the safe distance. But like this coming November, early and late November, I think we have a practice run and our hot fire that we're planning pending like weather and fire department permission and stuff. But it'd be good if you guys can come see what's up. I want to have you guys complete like a simple safety quiz to be aware of like what's going on, but like it's, I don't know, it's the fun part of the project. It's the payoff for all the work you put in. And one more note, the SPI and I2C devices are connected directly to the Raspberry Pi on the test stand. So we have sensor batch. So in our system, what we did was we decided to store all of our sensor data in a place where any program that wants to access it can access it. So in our case, we register an area in memory. So like, remember memory, how your program is only able to access memory from that's allotted to it. We tell the operating system, hey, give us this chunk of memory that any process who registers can access. And so what we do with that is we set this data structure in that memory location, and we have one program writing to those sensor values constantly. And then every other program that needs to read from sensor values simply reads from sensor batch. And it doesn't matter whether it's like the main program itself or another process or a logger or like the LabVIEW GUI stuff will have to read from this. All it does is, in the same way you read from another pointer, you're given the memory address, you register with EOS like, hey, I want to be able to access this too. It lets you do so. And then you like constantly read from this stuff. And one thing important, what volatile means is it's a keyword so that like when your CPU doesn't know these values and states are being updated outside of its own program. So often what happens is the compiler will make optimizations. It's like, hey, you didn't change this value between here and here, so I can just use the old value. I don't need to go all the way to memory to get it back again. What volatile says is this value can change at any time outside of your own program. So every time you reach for this value, let's say the second board temperature sensor in degrees Celsius value, you want to read that, instead of going to your like locally cached value, you go all the way to memory every time to guarantee that it's the most updated version. Okay, sensor monitor. This is our main safety and sensor control program, and it is run on boot. Every time we boot up the Raspberry Pi, it's the first thing that starts running. And we do this automatically using a thing called cron tab, which is a way for us to like schedule different programs to run at different times. We just have it run on boot every time. And so what it does, this is what does the actual SPI transactions to each of the devices. And the reason we have to do it like this is because, like before, we can only have one program doing an SPI transaction at the same time, because otherwise the chip select lines would be messed up and the data lines would be messed up. So like imagine doing a data transaction and then halfway through your data transaction, another process has to do a different data transaction, but the peripheral device doesn't know that they switched and you're still talking to the first peripheral device. You didn't switch. So then you get like half of one message and half of another, and it gets messed up. So that's the other reason we use sensor batch, is so we can have just like one thing reading all the sensors and then updating it in a like known place that everyone can read from. And so you see on the right, there's valve S amount, and we have shared mem batch is our sensor batch data structure. And then we have the like array value, and we write to 1,000 times the SPI ADC read voltage value. And so like the SPI ADC read, this is a function that does the SPI transaction for the ADC. Then we take that, we multiply it by 1,000, and we store it in this shared memory. And then we do that for all the valve feedback states. And we do that for all the sensors. And then we go through, and then we also do a pressure feedback loop. So we constantly monitor the PT pressure of 1 and 2. So in that case, that's LOX and ethanol, or I guess ethanol and LOX. And we check those pressures, and if they're too high, so again, here in sensor monitor, if that pressure is too high, then we bleed off some pressure. And then if it's within an acceptable range, again, we close that valve and like stop bleeding off pressure. So this is running all the time whenever the Raspberry Pi is on. And the last thing, or the other thing that's running, is also the watchdog. So this is the other reason why we wanted an external actual Arduino watchdog, is because like sometimes there might be other stuff running on the Raspberry Pi, and if the Raspberry Pi's load gets so high that it starts slowing down sensor monitor to the point where it's not like properly updating stuff in time, then we'll assume that's an unsafe state and we want to like reboot or like cancel everything. So that's the other reason. So like, again, if sensor monitor at any point stops working, then you see at the top pings, which is the ping the watchdog for the Arduino, that stops. And so the Arduino doesn't get a response to its ping, and then it reboots the Raspberry Pi. So this is like, we just want to have guarantees that we're at least running this. This is the main way we guarantee safety. One last thing is it has emergency stop lock. So in a program or in an operating system, there are things called interrupts. This is a way to sort of send a message from one process to another at a given instant. So there's no like timing constraints. You like, as soon as you hit it, plus or minus a small delay, it receives a signal and does something with it. And like, you don't have to put this in the loop checking. It's just you define a signal interrupt handler, which is a function that runs if you receive a given signal, and that'll, whenever you receive that signal, it'll run that function and then go back to wherever point in the program it was running and continue running. So in our case, we have sig user 1, which is defined by Linux as you can do whatever you want with it. And we made it so that whenever sensor monitor receives sig USR1 from any source, it's part of valve safety set. So what it does is it closes all the valves except the like pressure bleed valves, and it locks all the other, like it updates sensor batch with stop actuating flag, and then continuously sets these valves to the right state. But also this flag means that other processes that read this flag will know that, okay, I'm not allowed to actuate the valves. So this is a way to kind of like lock the valves and set them to a safe state given we're in an emergency, so we don't have like our process continuing to try to open and close valves when we're like just want everything closed. Like the example we give is like some dog or something ran onto the field as we're about to start a hot fire. So you press a button and then it stops the hot fire. It stops the valves from moving. If there's overpressure or some situation that does that, it bleeds those off still, but yeah. And we have it coded. We wrote a macro that runs whenever you open up an SSH terminal, and it binds the escape key to send SIG-USR1 to sensor monitor. We also have another script running on boot that whenever you're like, it waits for at least one connection, but whenever your number of SSH clients goes to 0, it also sends a SIG-USR1. So it's like, this is assumed that we lost control of our system because we don't have access to this SSH client. We have no way to control it, so we want it to be brought to a safe state. So this is done automatically. And yeah, it's run on boot. Okay. Pi Watchdog. I'll try to be quick with the stuff. This is code that is Arduino code actually, and it's run on our peripheral Arduino. And again, the Raspberry Pi and Arduino Watchdog talk to each other through USB. So what it does is has a timer. If the timer is greater than the given allotted amount of time, so I think it's like, I don't know, 2 seconds or something, then it reboots the Pi. If it reboots the Pi, or after you reboot a Pi, it takes a while for it to come back up. So we have it coded for, I think it's 80 seconds right now. So this is a little out of date. So it waits 80 seconds for the Pi to send like an initial acknowledgement to the Arduino again after rebooting. If this 80 seconds times out and the Raspberry Pi never successfully sent a message to the Arduino, we'll assume that it never successfully rebooted. So we reboot again. And we do this 5 times, and the whole time all the valves are set to off. So all the valves are closed and there's no actuation of them. We're just waiting for this reboot. Once we hit 5 reboots, we assume that something has gone critically wrong. Or once we hit 5 reboots without receiving a good signal, we assume something has gone critically wrong, and in such a case, it completely depowers the Pi, and the Arduino has 2 of its lines dedicated, like hooked up directly to the valves, to the, I think, bleed off valves. And so it opens those valves and just like keeps them permanently open and the Pi off, and then we'll have to investigate from there what went wrong by approaching. But we needed a way to be able to depressurize the system remotely, even in the event that our Raspberry Pi is completely dead, so that we don't approach something at like 800 psi and walk in, like open a valve and it blows off your finger. And then at the bottom is just like, if the ping is received, it's like, okay, good, you reset the timer and then you continue again. Contest 4, this is in Bash. This is a scripting language. So if you remember SSH, this is also what the terminal looks like when you're on a USB Linux system. So a terminal is the equivalent of CMD for Windows. It's just like a way to, if you want, you can open up CMD right now. Like hit the Windows key and hit CMD and hit enter, and it'll just be like a text interface for your computer. One thing is like the language it's using for ls and dot and stuff. That's Bash, and it's basically just a scripting language that lets you interact with the operating system's like Bash commands, basically. What this does is it checks the table of active SSH connections, and every, I think, 2 seconds, all this does is it checks the table of active SSH connections, and if it goes from an active SSH connection or any number of at least 1, if it goes from that to 0 connections, then it triggers the signal to sensor monitor. pkill or kill, it's a bad name, but it just means send a signal interrupt to a given program. pkill means send it to the program by name, so sensormon, and -10 means send it SIG-USR1. So by default, it's SIG-kill, which kills the program. But we want SIG-USR1, so we have -10. And this is the same thing that is sent when you hit escape. Another thing is that our SSH, both the server and the client, they're configured to have a very short, what's called keep alive time. So in the same way we have the Arduino watchdog, the SSH by default has its own watchdog. And normally this is like a 30-second or like a few minute watchdog where it sends like a nothing packet. So it'd be a internet ping where the data is just like 0 or something, or like a slightly different protocol maybe. It's just an acknowledgement like, hey, keep this connection alive, and I'll reset the timer. But what we did, we shortened that timer to like it sends every 2 seconds, and it checks the like receiving every, sorry, it sends every 1 second and checks the receiving every 2 seconds. So on the server, it checks every 2 seconds. If you've received a ping in a like within 2 seconds, then keep it alive. Otherwise, close the connection and update this list. But if the client, it sends a ping every second and says like, okay, keep the thing alive. I'm still here. So this is our way. We have an SSH watchdog as well as the Arduino watchdog. Latch. So in order to be able to actuate more GPIO pin or more like voltage levels than we have actual GPIO pins, we use a latch interface. And in the bottom right, I don't know if you guys have worked much with electronics, but basically, if you this isn't the exact thing we're using, but it's basically the same. If you ever want to know how a chip works, you type in the name of the chip and type datasheet, and it'll give you all the details of how the serial communication works. And that's the part we care about. Serial or parallel, whatever. The logic input. And here we have, there's 3 address pins, and then the data pin, and then enable, and we'll ignore reset for now. Basically, you disable the enable pin so that the output is not dependent on the input, and then you set the address. So with 3 address pins, you can have up to 8 like addresses, and this is simple binary. So A0 could be 0, 1, A1 could be 0, 1, or A2 can be 0, 1. And then you see at the top, first bit, second bit, third bit, those are the addresses. And you write to each of these. So like A0, A1, A2 are connected to the Raspberry Pi's GPIOs, and you write to the given address by setting those pins. And then you set the output value at that address high or low by setting the data line high or low. In order to be able to switch these and not have the like outputs change while you're changing the inputs, you use the enable. So you disable the chip first, but then the outputs will be whatever they were already at. This doesn't turn off the chip. This just disables the outputs from reading the inputs for a little bit, until you bring it back. So you disable the chip, you set your A0 and then A1 and then A2 and then the data line for whichever one you want, and then you bring enable back, and then the data line will update again, or the output will update. So simple example, if you want to actuate Q1, so Q1 might be valve 7 or something. Like, okay, I want to turn valve 7 on. So you say Q1, the address of 1 is 1, or it's 001 in binary. But from this perspective, it's A0 is 1, A1 is 0, A2 is 0. So what you do is Q1 is off right now. You disable the chips. So in this case, it's you write G1 and G2 high, I think. Yeah, that's what this protocol is doing. In this actual chip, there's 2 enable pins that, like, given if you set them a certain way, they like change the mode of the thing, but we don't care about that right now. You disable the chip, you set the address 100, and you set the data 1, and then you re-enable the chip. And then the disable enable is another digital pin. It's just like you turn this pin on and off. And then once you re-enable the pin, this Q1 will be on. And then by convention, you want to disable it again whenever you're not changing stuff. Sorry, whenever you're like not actively updating stuff, because it'll keep the 1 even when it's disabled. So latch funcs is the C library that we made, or like whatever program that we made that has all the like associated functions that do this processing. What it also does is in sensor batch, there is a list of current states. So like this is a internal tracking of the valve states that doesn't rely on any external hardware feedback. Just every time we flip a valve using the latch funcs, it also updates the flag in or the state in sensor batch of the given valve. Another thing is we have two versions of latch activating. We have just regular latch and master latch. Master latch always actuates the latch regardless of whatever, and it updates the value in the table. Regular latch, what it does is it first checks stop actuating flag to see if it's allowed to actuate a valve. So this is how we lock stuff out. So like if this flag at the bottom turns to 1, then latch is unable, it's disallowed from actuating the valves. So it's like it doesn't do anything, even if you call the latch update. And this is what we use in our hotfire scripts, so that even if the script is still running, if we set that lock on it, then the scripts can't actuate the valves. Then we have client monitor. This short answer, it reads from the sensor values and it runs a function to print them out, like in the bottom left, and then another function to save these to a log. So log sensor values. Pretty simple. The one thing to consider is there's a sync function. So in the operating system, instead of every time you say like save or like write to this file, and that's assuming this file is in the non-volatile memory. So that's on your hard disk. You want to save a file so that next time you boot up your computer, it's there and updated. What it does is, since writing to this file is a very, 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 very slow compared to like running in process, it batches all your requested saves in like chunks. And so if you say like, oh, okay, write to this file, it saves that in memory, not in, so it saves that in RAM or volatile memory. And it holds that there until its next given sync cycle, so that it collects all those at once and then loads them all in a big chunk into the non-volatile memory at the same time. And this is done in like a sync. So like if you call sync either in your command line or in the program, that forces that transfer from memory to non-volatile memory. But that transfer is much more efficient with big chunks than it is with like small ones, because like it'll take not the same amount of time, but it'll be much more efficient to do like big chunks of memory to move it all in a big block rather than do little ones. But what this also means is that like we haven't commented out right now because we're like, okay, it's not a big deal. But if we run our logger and we are collecting values, but then something goes horribly wrong and it like our system reboots or something, or like the system explodes and like we need to fish out the like SD card or something, there's no guarantee that the sensor values leading up to that explosion will be on the chip or on the SD card, because like there's no guarantee that the sync was called. So we thought like we could force the sync every so often to give like a certain amount of updated values. For now, we assume that like we won't really need, like we won't encounter that situation. In the future, it'll be useful if we ever get into a situation where we really need that last like second or 50 milliseconds or something leading up to something going catastrophically wrong. But for now, we're like, all we want is to be able to log values for like analysis later, assuming things go right. It's currently not too built to do like the very deep investigative diagnosis after something goes wrong. That might be something that one of you guys does at some point in the future. Rocketry load cell. I hate the HX711. It's a chip with its own custom interface, so it's not SPI or I2C. So it has its own data and clock line, and it does it in its own weird way. I tried writing my own interface for it, but there's like a whole lot of timing and like update and multi-threading stuff that kind of made things complicated. So I'm like, okay, we'll find one online. There was one online that it was using a different GPIO library interface than us, which meant we couldn't use it for our program by default. So what Devin ended up doing is finding the older wiring pi version and having to modify it to be able to fit with what we're using. So when you see the HX711 library, it's like 3 files from that library that have been modified to be able to work with our system. And I haven't tested this so far, but it does, in theory, it should do the same thing of like getting the sort of registering to be able to access the shared memory, getting the pointer for the shared memory, and then every time in the loop, it reads the weight of that load cell by like through this library. It does the sort of serial transaction. And if you want to know about the transaction itself, you can look at the datasheet for the HX711. What it does is it gets the formatted value in grams of the thing given this calibration value, and this should be offset and gain, I think. And we'll need to calibrate these outside of this program, and that'll be something that we'll have to do. Ideally, we only have to calibrate it once, but it might mean our load cell sensor values have some error in them, but just kind of have to live with it. Unless one of you guys want to do it. This will be important for the cryo module guy. I think G. I think you guys said you were working with the load cell. Oh, Devin.
Yeah, I was just gonna say that we're gonna be using this, or we separated it because it's because the HX711, I think its max rate is 80 hertz, which is super slow. And I'm just reading this on the left side now that you have already written it here. So my bad.
It's okay. I didn't read that either. But yeah, what Devin said, 80 hertz is 80 times a second. Doing something 80 times a second in real life to a human is fast. But when we compare it to the 2 megahertz, so 2 million times a second of the like SPI stuff, or like technically the like hundreds of kilohertz or something of the actual samples, this thing is slow. So we couldn't put it in sensor monitor because it would like spend all of the like clock cycles of sensor monitor just like doing its own thing. Basically, the majority of the time would be waiting for the like chip to respond, basically. So we took it out. We have it running as its own process, and this is also running on boot. This is a really new addition, so we'll have to do some testing. I really hope this works. But yeah, basically it's a program that is the load cell software interface running by itself. And if you see load dat, load CLK, and like here, or not here, I guess in sensor monitor, there's like PTS amount, PTCS, I2C array. So these are hard-coded, what are called macros. So they're not variables, and they won't change during execution. But in sensor batch, technically above, I'll show you guys later. These are just like, these are values that we tell the compiler like every time you see f or SV underscore FB underscore CS1, that means the solenoid feedback chip select 1 for that ADC, and that GPIO pin for wiring pi is hard coded in sensor batch. And so that way we can just like define these and like change them all in one place. And all these programs that need to read from this and stuff, they all read from the same numbers. So we don't have to manage like 50 different versions of the GPIO mappings. The last thing, hot fire scripts. So this was all in order to like be able to have like really simple and foolproof like hot fire scripts, so that all our safety stuff is running in the background. So we have our fire procedure. All it does is it has some like prefix setup or whatever, but all it does is it closes the 4 latches or 4 SOV valves, waits half a second, opens up hand valve 4. So that'll be it's not too important, but it should be, I think, this valve. So it opens up the locks. And then waits another half second, opens up ethanol, and then waits 2 seconds and then closes both. And then at the same time as it closes both, it opens up the nitrogen purge and purges for 3 seconds and then closes it. We don't currently have the igniter ready. We're waiting on the propulsion team to get their igniter sorted. But basically this would burn for 2 seconds our rocket engine, and then close it, and then ideally purge it, and then we'd be happy, hunky-dory. Pre-chill, since we don't want the liquid oxygen to touch the walls of the exhaust and instantly like vaporize and like cause a whole bunch of pressure, back pressure in the system, we want to be able to chill it first, so like it's not as violent. So what it does, we close the SOV values, we open up the hand valve 4, so that's the locks line, and then open it for half a second and then close it. Same with, or okay, press F and press locks. What these do is these are loops that they open up the locks or ethanol pressurant lines, so that'll be SOV2 and SOV1. They take pressure from this nitrogen tank and they pressurize the tops of the locks propellant tank. Yeah. And so it creates pressure in the locks tank so that when we open up the valve to burn, all that locks just gets shot out. And we want to be able to hit like a specific pressure value. So right now we have it so you in a loop read from sensor batch for the PT value for the appropriate PT. And then if that value is above 515 PSI, we close the valve and we assume like, okay, we got our pressure. Right now, these are both coded for 515 PSI. We'll have to talk with the propulsion team about that. Okay, so that was a lot of stuff. Actually, first I'll show you really quick the sensor batch thing. So this is our GitLab repo. It's kind of messy. We have a lot of stuff in it, but like, I don't know, don't be afraid to check stuff out. I'm in the process of getting repos set up for all of you guys for your sub projects. I'll get that out sometime soon this week, ideally. And I'll give you guys access and like I'll send you guys some tutorials on Git. If you've never used Git or GitLab, I'd recommend checking out some YouTube videos. But here are the like definitions. This is all based on our like hardware. Okay. Yeah. For now, hold it on GitHub. I'd like to keep them all in the same place, so we'll transfer it to like this product at some point or project. But for now, you can keep working on that. Git should be able to track everything. Anyway, these are like hard coded, and when you compile it, these aren't variables you can change. The compiler just reads like 6 in every place that you'd put SOV1. And this is based on our current like hardware setup, and like the GPIO pins, the number of different sensors, the locks, safety, pressure values and stuff. The SPI speed. Right now it's set to 500 kilohertz. We want to bump that up. Okay, so questions, comments, concerns. This was a lot to cover. And it's okay if you don't like remember everything exactly. Like you can always like look online or refer back to this video or whatever else. But I wanted to get you guys introduced to some concepts related to embedded systems and like real-time control systems, whatever. And also how our system solved it. So you can have an idea, if not to interact directly with it, then like how it's been done before. Yeah, I don't know. Do you guys have anything to comment? Like, you guys have your follow-up plans with it. What you want to do? I want to meet with the RF guys sometime soon and the environmental control. So set a meeting with me. This meeting was recorded. I'll be uploading it at some point, either on YouTube or something. Otherwise, if you see me on campus and have questions or want to talk to me, feel free. That or on Slack or whatever. But I think that's everything. Yeah. Yeah. You can stay after the meeting if you have more questions, but for now